Satellite motion. This is a bit of review from what we did last day. It'll be quick, and then we'll go on to friction. Satellites. How many satellites do you think there are around the Earth right now?
3,000.
Declan, say that again?
3,000.
It's about 3,000, more than that now. But.
Yeah.
And it also depends if you count all the Starlink ones. You know about the Starlink satellites?
Oh, yeah.
Who here knows about Starlink?
Try and close it down.
Who does not know what I'm talking about?
Unfair competition.
Okay. So Elon Musk has SpaceX, and one day they were like, you know, it'd be nice to have internet when we go out to like remote locations or something, and for people with cabins or and to give Africa internet. And so they said, well, we have a space company. Why don't we just send up some satellites and we'll build some Wi-Fi, transmitters. And so they did. So they've launched now, like 1,000 or something. There's going to be apparently 60,000 of these little bricks that crisscross the Earth, and they will basically bathe the middle of the Earth with Wi-Fi, and you can buy it now. So if you take each of those as an individual satellite, it would be more than that. But in general, 3,000 to 4,000 satellites up there right now. Declan?
Already? An absolute hassle to launch a rocket and not hit one of those 16,000 cubes.
You would think so.
The Earth is super big.
The Earth is super big, and there's a lot of space up there. And so there's also there are different orbits, and so we have orbits like an altitude for commercial satellites, and we have an altitude for military ones, and then there's the Wi-Fi ones are actually quite low. And then there's other military ones that we probably are there that we don't know about. Let's carry on. So, let's talk about the moon. Is the moon a satellite?
Yes.
Yeah, technically it is. It orbits the Earth, so it's a satellite of the Earth. Mass of the Earth, 5.98 times 10 to the 24 kilograms. The moon is about 100 times less massive than the Earth. If it's 100 times less massive, why is the gravity on the moon not 100 times less? What happened to the size?
Oh, exponential stuff.
Right, so the Earth, we're a long way from the center of the Earth, right? When you stand on the moon is quite a bit smaller, so you're closer to its center. And so the gravity is less, but not as much less as you would think based on the mass. So find the force of gravity between the Earth and the moon. Go.
Wait, what's the universe?
6.67 times 10 to the negative 11.
Good.
Yes, it is.
6, 7?
So that you know on the video, we're gonna watch the videos on Friday tomorrow. Last time, and we're gonna do friction next,
How far is it?
and there's a quiz tomorrow.
Oh, that's up there. No, the range is 35.
No, I'm gonna put this under here, sorry. Do you think we have to worry about the radii, the two radius of the Earth and the Moon?
No. The distance between them.
The distance between them is so much bigger than the radius of each object that we don't really need to worry about the radii. Don't forget the square. Don't forget when you put it into your calculator, use the E. If you haven't found out how to do that yet, you cannot survive this course without knowing how to do that properly in your calculator. So ask me today. Just put your hand up if you have an answer. Okay, put your hand up if you need another half a minute. Okay, I'll give you another half a minute. Did I do that right?
Yeah.
Yeah.
I'm gonna write this bigger so people can see.
Oh, no, I just wanted that. No.
If it takes you a little bit longer, don't worry. This is, make sure of it, and this is about learning how to do this. I've done it lots of times, so I can do it quickly. The answer you should get somewhere around 2 times 10 to the 20 newtons. A little bit of force or a lot of force?
A lot.
It's a lot of force. So, why does the Earth why does the moon not fall into the Earth?
Initial velocity.
Because it's straightforward. It's straightforward. Velocity is higher.
Huge amount of force. Huge. Huge. Big mistake. Huge. That was from a movie. Anyway. The moon, why does the moon get pulled in and
It's moving straight. And it's just caught from
the moon is in orbit around the Earth. An orbit is a perpetual motion. This seems to defy the laws of physics. Because here, right here, I can't make something with perpetual motion.
Doesn't it eventually stop?
Does it?
Well, not in space.
There is actually no reason in the laws of physics why the moon should eventually stop. It will keep going. Because there's no friction in space. Now, to be honest, the moon is actually slowing down. It's getting further away from us. There's a reason for it. There is some friction, but not in space. It's actually happening right there if you go down about a kilometer or so.
The ocean.
The ocean. What happens in the ocean every day? Tides. What causes the tides? The moon's gravity and the sun's. As the moon goes around, it's not really as the moon goes around. As we spin, the moon pulls the water, the ocean water, towards it, right? And so you get this bulge of water here and not over there. And that's why we just see the ocean water coming up and down, right? That's because of the Earth's gravity. There is friction in that movement of ocean water, right? And that actually does take energy away from the moon and it slows it down. 10 million years ago, the moon would have looked much bigger,
How much bigger though?
quite a bit. The moon used to be a lot closer to the Earth. And over all those years of pulling the tides up and down and up and down and up and down, the moon has actually slowed, and when it slows, it gets farther away from us. That's not really something you need to know about. So why? Let's just go back to the normal thing. Let's say that movement is negligible, and the moon is just going around the Earth, and it just doesn't stop. Why can it be in perpetual motion? Why can't we use that here for some, to get energy?
Because our
Friction.
masses.
Yeah, it's basically friction, right? If I have a motor, I have some motors in the back, I should bring it up. But if you have a motor and you crank it up, and then you just release it, the crank will go for a while, right? So can I get any energy out of that? Yeah, if you crank up a motorator, if you crank up a motor, it turns into a generator. You get electric energy out the end. And we have lots of examples of that. Most of our electricity that we have here, we get from hydroelectric power, right? The sun heats up the water goes in the sky, clouds, rains, river comes down, dam, goes down a tunnel, turns a turbine. So the water's turning a motor, and we're getting electricity out of that. It's a dark day, the school's lights just came on. The school thinks it's nighttime. It's so dark outside. Anyways, what do you need to keep that motor spinning?
A force of some kind.
Good. You need a force. So the water provides that force, and the energy from that water originally came from the sun. If you crank up a motor, you have to keep pushing it. If you want to get energy out the end, you have to provide work. You have to provide energy. We get that energy from our food, which originally got it from the sun. So everything is kind of solar power, but the moon no one is pushing the moon, right? That's because there's no force against it. Relatively small as we get the tides, and we do use that in some places for getting electrical energy, but it's a small amount compared to the energy that the moon is going through, exerting. Okay, so the moon can be in pretty much perpetual motion because there's no force acting against it. It doesn't need a force to push it because there's no friction. Does that make sense?
Yes.
Okay, moving on. Okay, that's great, but how does a moon get into orbit? How did it happen in the beginning? Ashley's got her hand up and I'm worried. Okay, Ashley, tell us.
Well, so the Earth was there originally, and then no.
Okay, so the Earth was there.
Okay, and then an asteroid or whatever, went across, went straight forward, and it caught the Earth's gravitational kind of orbit.
Okay.
And so it's still moving straight, but because it was caught by the orbit, it continued to circle. So it's still moving straight, and the only reason it's orbiting is because of the Earth's gravitational pull. That's how I understand it.
Yeah, that's a pretty good understanding. You're missing one important event.
The Big Bang.
Well, not that far long ago, but the moon actually hit the Earth. There's a part of the moon came from the Earth. We know that. We've looked at the composition of the moon, and we know that there was an asteroid. You're right. There was an asteroid that came and it hit the Earth and went, and it took a glob of the Earth off of it, and it flew out into space and then eventually kept going. But we think it hit the moon, or it hit the Earth first. Yeah, but you're right about in general. Do you know where the Earth came from?
There's a
yeah,
whole
I
other
think
space,
so.
asteroids like hitting.
Declan,
Yeah.
tell me.
A bunch of like asteroids and stuff they mashed together over.
Do you know where the sun came from? Connor?
Hydrogen.
Connor, tell me.
The Big Bang. A lot of atoms coming together.
The sun was actually quite a bit after the Big Bang, we think. Is yeah?
Oh no, I just have a question.
Okay, shoot.
What would we do if like another massive asteroid came?
Got a video for that.
We
Remind
just
me.
shoot a nuke
Can
at
we
it.
see this?
Don't let me forget.
It could be like Galaga.
It's one of my favorite. It's not. Yeah, it's like a favorite.
I don't know,
video.
hold our hands.
Alright, so.
Who likes football?
I was your top.
Anybody like football? Connor, let's go, Connor.
No, I get hot.
This is how I see you, Connor.
I would do hard notes.
Just do a row.
Okay. Connor is gonna throw a football, and when he throws it,
Connor gotta get her
Can't really tell if that's my hair, if that's a hat.
I have a football in here somewhere. If Connor throws a football, what's gonna happen to it?
It's gonna go up, and then it's gonna stop, and then it's gonna go down.
It's gonna fall, right?
Yes.
Why does it fall?
Gravity.
Okay, good. Gravity's pulling it down. Why does it curve when it falls?
Because it's going up, it's throwing,
Is it because he's throwing it? What if he throws it flat?
We're still gonna go down.
It's still gonna go down? Okay, but why doesn't it go, have you ever thought about this? Why does it not go like that? Like, isn't gravity pulling it right from the beginning?
Because the velocity at the start.
Velocity at the start? Okay, what do you think about the velocity here as compared to here?
Well, there's a force maybe like acting.
There's a force? Okay. When does the force act?
After.
When you're throwing it, right?
No, like yeah, like the minute you let go.
Oh,
Seriously, I have a
resistance
football.
lifts up the ball.
Can anybody see the orange football?
No.
Here's- This is the best I can do.
Oh.
This is a medicine ball. Okay. I'm gonna throw it. Ready? This is gonna be dangerous. I might hurt myself. If you throw
tennis ball.
while it's touching my hand, my force is exerting, right? What about when it leaves my hand?
No more
Now
force.
No more
it's
force, right?
But
gravity.
it's still.
There's a little bit of air resistance, so it's gonna slow down a bit.
And
But
gravity.
especially with this guy,
Use a tennis ball.
he's not gonna
We get more
do much,
control.
right? So you notice it curved, right?
Yes.
That's kind of weird. Why does it curve? Why doesn't it just, like, gravity's pulling from the beginning, why doesn't it just go straight?
Because
Another
the
initial
initial
force.
force.
Adam.
Isn't it like the acceleration of gravity? So
Ooh.
9.8 and then
Good, very good. Adam says there's an acceleration. In which direction is the acceleration?
Down.
Down. Because gravity is pulling down. What's happening to the velocity in this direction?
Remaining the same.
It's pretty much the same. So if an object stays the same velocity horizontally, but is getting faster on the way down, it will curve. You understand? Thank you, Connor. Okay, now, imagine you have the Earth. I may have told you guys this before already. Here's a mountain. This is the Earth. It's not a very great Earth, but whatever. Okay. And if you stand on top of that mountain, and let's say you have a cannon. This is what Newton imagined. This is a cannon. And you fire a cannonball out. And it goes, right? If you fire it faster, it'll go farther, right?
Yes.
But if you fire it fast enough, the curve of the Earth is such that the ball will fall, but it will just keep on falling. And eventually will come back in place. And this is orbit. The misconception is that things in orbit are just floating up there. Falling. They're just... Say that again, Matthew?
You're falling.
Very good. They are falling. Right now we are falling. What are we falling into?
The sun.
I don't know. I don't know. Who said the sun? Matthew, good. We are right now falling into the sun, but we never get any closer because we're also moving laterally, right?
So we're also not.
Once upon a time, there was this cloud in the universe. Gas, dust, atoms spread far out. 2 atoms went like this. Boop. They touched each other. And now they're 2 atoms. And because they had a little more gravity, there was a 3rd atom, and it went. Boop. Now it's 3 atoms. Fast forward 1 million years. It's like 100 atoms. Can't even see them. Fast forward another 1 million years. There's a little clump, like a breadcrumb. Fast forward another 1 million years. We got a gravity's dust, is it? Fast forward another 1 million years. Bigger clump. Fast forward another 1 million years, and you got this. Now things are really falling in. Ever open the drain in the bathtub? What happens to the water? It starts to spin. And this, as it's pulling stuff in, starts to spin a little bit. Fast forward another 1 million years, you got like West Vancouver size, and stuff is like, and it's pulling stuff in, and you get more gravity, and stuff's, and fast forward another 1 million years, you got like a planet-sized thing, it's, and there's big gravity, and things are getting crushed in the middle, and there's more, and then big cloud, and all this, and 1 million years more, you got like 100 Earths, and it's like, and it's spinning around, and it's pulling stuff in, and it's like this, and then there's so much gravity in the middle. There's so many atoms piled on top of each other. The atoms in the middle, they go like this. They go. Do that with me. Yeah, you can do it better than me. And 2 hydrogen atoms go. And they become a helium. And a little bit of that mass turns into energy. And you get light and heat. Photons shoot out of it. And a whole bunch more do that. Now you have like light and heat spreading out some fire and every once in a while there's so much heat and bubbling and something gets thrown out and it goes out from it, and sometimes it gets thrown out, but there's so much gravity it goes back into zero. And sometimes it gets thrown out so fast there's like off into the universe and it's still out there somewhere, it's hardly gone. And sometimes it gets thrown out and it gets pulled back, but it gets pulled back at just the right velocity so that it just keeps falling. And that's what you're standing on right now. You're standing on a little glob that was thrown out from the formation of the sun. Do you ever have soup and the next day you like left it somewhere and the soup has that little skin over the top?
Yeah.
That's what you're standing on right now. It's the dried crust around a ball of sun juice that is orbiting around this thing that was this conglomeration of cloud of dust that came together because of the force of
Gravity.
gravity. All came from gravity. That's where the Earth came from. And we're still circling around the sun in this nice little recipe. So the football is still being proven, so it's starting to show speed, orbit, and blah, blah. All times, ball is being pulled towards the Earth. So if you have the sun, this is the sun, and you have the Earth, this is not to scale. Here's the Earth, and we're moving like that. What is the direction of our acceleration?
Forwards.
No. Down. I'm glad you said that, though. What's happening to our velocity forwards?
Constantly.
Yes, it's constant. The forward velocity is constant. Well, okay, so you have this velocity. If the sun were to disappear, if it just like whoop, Thanos, just it's gone. We would end up flying straight, right? There'd be nothing pulling us toward the sun, so we would just go straight. But the force from the sun is pulling in, yes? And so we are accelerating towards the sun all the time. We're still falling towards the sun at the same acceleration that we would be if we were not moving, we just fell into the sun. But because we have this velocity going this way, we end up moving. We go forward a bit, and then we go eep, a little bit towards the sun. Then we go forward, and then we go eep, a little bit towards the sun. Forward, and we end up with this curve, just like the ball when you throw it. We have a constant linear velocity, but we're being accelerated towards the sun. This is really centripetal force. It's a force toward the center of a circular motion. Does that make sense? Because I just said objects in orbit are in free fall, because we are falling, always falling towards the center of the Earth, but never reaching it. So how come in the International Space Station, you're up there, you see those men and women up there? There's people up there right now. I was wondering when you were going to skip that. Peer pressure. I feel like I should get mine on too. They're just floating around up there, right? Why are they floating? Is there no gravity up there?
Oh, because there's no spinning.
There's no.
There's no spinning.
Well, they're not spinning, that's true. Are they revolving around us?
Yes.
Yes. So how come if you're in a space station, how come you're floating? How come you're not being pulled towards the Earth?
Because the gravity in the ship, like, there's not enough.
Lilia, what do you think? I can tell you're thinking about it. Okay. Is there gravity up there, do you think?
Yes.
Okay, less than here, for sure. But would there be a force of gravity? Yes. Yes. Ainsley?
Because they're moving at the same velocity as the International Space Station, which, so they're still going.
Right. So they are falling towards